this is the right homework. We can go through problem 2 real quick. Let's get this snipping tool. Let's throw that right here. Yeah, if it's all right with you guys, we can go through this real quick. It's always good to keep practicing and review. Okay, so give the complete homogeneous solution. So we have a second order system here. You can tell by the highest order of the derivative. So the highest order derivative is 2. So this is second order. And the number of initial conditions you have is always equal to the order of the system. So you need 2 initial conditions. So the way to solve this is first, what I do is I substitute an expression for the homogeneous solution, and it's always going to look like this: some coefficient times e to the lambda t. It doesn't matter what order of the system it is. You always take this and you substitute into the original differential equation. So I'll call it a diff EQ. Okay, so let's do that. So if I take 2 derivatives of this, that'll be the first term. So it'll be lambda squared a e to the lambda t plus 2 times the first derivative. So that's just 1 lambda out in front, plus 10 times that original function itself. And then what I do is I divide both sides by a e to the lambda t, and what you're left with is called the characteristic equation. So if we divide all this out, it's just going to be lambda squared plus 2 lambda plus 10 equals 0. And you know what? Once we, probably even on the next homework, you can just jump right to this step. Like if you look at a differential equation, the characteristic equation is always going to be like, okay, 2 derivatives for x, so that's a lambda squared. So I guess what I'm saying is you can basically just write the characteristic equation right away and just skip to that step. So then you get roots of the characteristic equation. You can use the quadratic formula to get these roots, but I'm trying to teach you guys some basic MATLAB commands as well. So what I would do to get the roots is I would go over to MATLAB and use the roots command. So it's the roots of lambda squared plus 2 lambda plus 10. So that's like how you write that polynomial in MATLAB language. Lambda squared plus 2 lambda plus 10. So the roots are -1 plus or minus 3i. So there's 2 roots. So I'll call them lambda 1 and 2 equals -1 plus or minus 3i. So we call this a complex conjugate pair of roots. And we're going to go through second order systems in a little bit more detail today. You don't always get a complex conjugate pair of roots with a second order system. When you do get a complex conjugate pair, we call it an underdamped system. So, okay. The general form of the homogeneous solution for a system with complex roots, general form of homogeneous solution, if you have complex roots, it's this. I'll just call it x homogeneous of t is going to be e to the minus 1 times t, and this minus 1 is coming from the real part of the root. And then we multiply that by a1 cosine 3t, or you can just call this coefficient out in front, whatever you want. It's just a constant number, plus a2 sine 3t. And this 3 is coming from, you guessed it, the imaginary part. So that's your general form. So this problem asks for the complete solution. So the complete solution just means that you solve for all of these unknown coefficients in the general solution. That's all that getting the complete solution means. It means like specifying every parameter in the general solution. So the way to do that, complete solution, you use the initial conditions of the problem. So what are our initial conditions? So x0 equals 1, and the other one is x dot 0 equals 1. So, okay. So we'll use each of these conditions separately, but I can plug this one right into that general form we have up there. So x0, it equals 1, and it's going to be equal to this whole expression with t equal to 0. So it's going to be e to the 0 times a1 cosine 0 plus a2 sine 0. Sine of 0 is 0. E to the 0 is 1. Cosine to the 0 is 1. So this just means that 1 equals a1. And so you would be able to take this parameter and substitute it up there, right? Then to use the other initial condition, I have x dot 0 equals 1. And that's a little bit trickier because you have to take the first derivative of this. So that's negative e to the negative t a1 cosine 3t plus a2 sine 3t plus e to the negative t minus 3a1 sine 3t plus 3a2 cosine 3t. Oh, so this is only equal to 1 when I set t equal to 0 though. Yep, homework 2, number 5. We were just talking a little bit about homework 2, seeing where people had any questions or concerns. And we're just taking a little bit of time at the beginning of class to go through it. So if I set t equal to 0 in here, I'm just going to be left with, let's see, minus a1 plus 3a2, if I did that right. So that means A2 would be equal to A1 plus 1 over 3. And we know A1 is 1, so this would just be 2/3. Is that what you guys got? Nope. Did I mess up or did you mess up? Okay. Okay. Some people got what I got. You got 0? Is it okay if you got the same answer using Laplace transforms? That's fine with me. We'll get to that later in the class. You got 2/3 for that other coefficient? Okay, enough people are agreeing with me that I'm feeling pretty good. I do make mistakes. It's not unheard of. But I think this is right. Unless I screwed up. All right. After class, if you have other... Where's minus e to the... Oh, this is because... So this is the first time derivative of our general solution up there. So you got to remember you have e to the minus t times this other function of time, like this a1 cosine stuff. And you have to use the product rule. So you take... Okay. Gotta remember the product rule. If you have more questions about homework 2, let's wait until after 4 p.m. today. We can go through it. But we have some new stuff to cover. Let's turn this music down a little. All right, I like to start with a recap. Okay, so we've done 2 physical examples of dynamic systems so far in this course. The first one we looked at, it's a first order system. It's an RC circuit. So the R stands for resistor, as you know. The C stands for a capacitor. And this is a way to draw the schematic for it. We have a source voltage, which I was providing from an Arduino, and then it goes through a resistor, then it goes through a capacitor, and that completes the circuit. And we could even throw the current going through here. And from homework 1, it looks like most everybody has a very good understanding of how we do some basic loop rules. Check your homework, see the comments that I put on it. There were a couple of us who mixed up the voltage drops on these. So make sure you figure that out. And here is the homogeneous response. If so this vertical axis is the voltage across the capacitor, and this horizontal axis is, if my pen will write, it's time in seconds. So if you charge the capacitor up to 1 volt and then you just set the source voltage equal to 0, then the capacitor voltage drains like this in an exponential fashion. If you do the loop rule, you can set up a differential equation that describes these dynamics that looks like this. So if you're going to analyze this differential equation, first we always set up the characteristic equation. So if I skip some steps here, that's our characteristic equation. Lambda plus 1 over RC equals 0. If you solve for the root, which is lambda, this is one note. Checky. Lambda is minus 1 over RC. So this is just a real number. Anytime you have a first order system that has a root like this, the general form, I won't use X, I'll use V. So the homogeneous solution I'm using a Microsoft Surface, just with the pin that comes with it. So the general form is you have some coefficient and then e to the lambda times t. Danke, in the market. Yeah, I love the Surface. I give it a high recommendation. So if I plug in minus 1 over RC for lambda, I get this. And this is what I'm plotting up here. So it's exponential decay. It's what we actually measured. Okay, the time constant. The time constant is a measure of how fast your system is. So in this case, it's a measure of how quickly this capacitor can charge or discharge. The time constant is always related to the real part of the root. Well, in this case, we just have a real number for the root. But the relationship is this. Tau, the time constant, is minus 1 over the real part of your root. So it's going to be minus 1 over minus 1 over RC, which is just RC. So if you want to know how fast your capacitor charges in an RC circuit, you take the resistance, you take the capacitance, and you take the product of the two. So in the circuit that we did in class, the resistance was 1 kilo ohm, the capacitance was 1 millifarad, right? And if you multiply that together, it gives you a time constant of 1 second. Okay, so that's a time constant. The settling time is defined as 4 times the time constant, or it's the time it takes to get 98% closer to your final value. So this voltage starts at 1. By the time it gets to 0.02, once it's drained that much, it's reached 98% of the way to being drained. That's the settling time. So for an RC circuit, it's 4 RC. Okay. Let's talk about our next system that we did. We did this on Friday. We did the response of a pendulum. Let's zoom in on it here. So here it is. I just had it hanging off the end of my desk, and I would pull it to the side, and then when I release it, it goes back and forth and back and forth. And here on the back end, we had a rotary encoder, and that just measures the angle as a function of time. And so here's a schematic. You could draw like a free body diagram on this. You know, you have the weight of the pendulum acting there. And we went through the steps of Newton's laws. So my rotary encoder, I had it measuring this angle relative to vertical. And this is what the response looked like. It goes back and forth, back and forth. You guys know how a pendulum works. So it's sinusoidal. It oscillates. And further, if you make the envelope function on here, you see that it decays with time. So no pendulum on Earth is just going to go back and forth forever. Energy slowly leaks out of the system because of a little bit of air resistance, a little bit of friction in the joint. All right, what's our differential equation? I have to pull that up. I don't remember it off the top of my head. There we go. Where are you? Oh, here we go. This one's going to be second order. 1/3 ml squared theta double dot. So that's the second time derivative of the angle of the pendulum is equal to, actually let's write it like this, plus c times theta dot, that's like the friction in the system, plus L over 2 mg times theta equals 0. And we plugged in numbers for the mass, the length, that damping coefficient, because I had measured everything in advance. So how about we write that out real quick? You get, and I'll divide by 1/3 ml squared, so we'll just have 1 in front of the theta double dot term. 0.0215. So that's our differential equation. So let's go through the same steps here. Let's get the characteristic equation, the roots, settling time. Let's get some information about this. This is the characteristic equation. Skipping some steps, but that's what it is. If you solve for the roots, you can just use the roots command in MATLAB to get that. You get this. So now we don't just have one root, we have two, and it's a complex conjugate pair. And now this is just like the fifth problem of homework 2. The general form here is going to be, how was C determined? Great question. What I did is I ran an experiment. So C is the, it's that damping parameter right there, right? I ran an experiment to see how the system decays over time. And there's a technique called the logarithmic decrement method. And basically what that does, it looks at how quickly the peaks decay over time, and it lets you backtrack what's called the damping ratio of the system. And we're going to talk about the damping ratio today. So I experimentally determined the damping ratio, and then from there I determined what C is. Fantastic question. Okay, so you have E minus 0.0108 t. So this is just the general form when you have complex conjugate roots. Anytime you have roots that look like this is the general form. It's just a matter of figuring out what these coefficients are, which you can use the initial conditions to do. T. All right, and we did solve for these coefficients on Friday. What happened to that last theta in the differential equation? Oh, very good call, my friend. That should still be there. Thank you for pointing that out. There should definitely be a theta there. Okay. Time constant and settling time of a second order complex conjugate system. So before I told you it's related to how quickly the envelope decays to zero. Fortunately, we solve for this just the same way we would for a first order system. So tau is minus 1 over the real part of the root. So we have minus 1 over minus 0.0108. Let's figure out this number. I'm going to bring it over into MATLAB. So 1 divided by 0.0108. Oh, buddy. That's 92.6 seconds. Now, we didn't actually calculate this last time, but you could ask yourself, how long does this pendulum take to finally come to rest? Well, that's what the settling time is for. So my settling time, which is theoretically when it decays 98% of the way, which is effectively it's done, would be 4 times that. 370 seconds. How many minutes is that? Like a little bit, like 6 minutes? That's kind of hard to believe. I guess we could test it. I don't have the pendulum set up today, but this is telling me I can just let it swing over there for 6 minutes straight before it dies out. But that's one of the powers of these models. You can answer questions like that. I have never run the experiment where I just let it go forever for the purpose of trying to calculate how long it takes to decay. That would take a long time. Is it possible to have a negative time constant? No. It is not. Well, actually, this is, I'm really glad you asked that, because that goes right into our next topic. System stability. Okay, here we go. A system is stable if and only if all of its roots, and I'm talking about the roots of its characteristic equation, have negative real parts. And this actually answers your question, MJ, in a way. So a system is stable if and only if all of its roots have negative real parts. So what does it mean to be stable? It means that if you're a first order system, no matter where I have you start, your homogeneous solution is eventually going to go towards 0. Even if I start you at like a negative value, like down here, If I let it go, it'll go back to 0. Even if I start it like at a higher number, blah, 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 it's going to go to 0. So this is stable behavior. What does a complex conjugate second order system look like if it's stable? Same kind of thing. If I start it over here, it'll oscillate, but it just tends towards 0 eventually again. You only see a stable response like this if the system has negative real roots. And this is why the characteristic equation is so important. Because we look at the roots, if all of the roots have negative real parts, we know the system is going to be stable. What does an unstable system look like? Well, you might start it here, but it's only going to get farther from 0, and it's going to go faster and faster and faster, running away from 0. If you start at negative, same thing. It's like, I want to stay as far away from 0 as I can. A practical example, if we had the Dragon trying to dock at the International Space Station, and if the autonomous controller was unstable, boom, that thing would just shoot away into space. It would never dock. If you have a second order system that I started here, it would do this. The oscillations would get bigger and bigger. So very easy to determine if a system is stable or not. You look at the real part of the roots. So the only way you could have a negative time constant would be if you had an unstable system. And then the time constant makes no sense, because the time constant talks about how quickly you go towards a final value. Well, you don't go towards a final value if you're unstable. You go to infinity. And you just keep going farther and farther away. So time constant doesn't even make sense for an unstable system. So you can never have a negative time constant. Okay. Today, we're going to get into more details about second order systems. So far, I've only showed you an underdamped second order system, a pendulum. And so you have an idea in your mind of what its behavior looks like. But there's 3 other types: undamped, critically damped, and overdamped. So I want to introduce those to you today. The way to do it is we start by looking at a standard form for a second order system. So you can always write a second order system like this. Let's define some of these terms. So you see this zeta in there. That's called the damping ratio. And in fact, the damping ratio is what all of these classifications are based on. Omega sub n, that's the natural frequency. Omega sub d, you don't see it in this equation up above, but it's related to these first 2 parameters. So it's called the damped natural frequency. And this is how it's related to the natural frequency. Omega d is the natural frequency times the square root of 1 minus the damping ratio squared. So this is the standard form. These are the variables in that equation. And we'll talk more about them as we go. All right. What we're going to do is we're going to break down this general form of the equation like we've done with the other differential equations so far in this course. And then we're going to draw some conclusions from it. So, all right. The general form from which all other general forms stem from. Well, this is a homogeneous equation, so I'll just put a sub h here. But it always looks like this. Even the complex conjugate solutions, we showed that you can derive it from this exponential. Like a sine and a cosine is a exponential to a complex number. So this is just the most general form. So we substitute this into this differential equation up above. So I'm going to have lambda squared a e to the lambda t plus 2 zeta omega n lambda a e to the lambda t. Zeta is really hard to draw, by the way. I've been doing it for years and I still can't do it consistently. All right. But we took that general form and we substituted it in up above. Now, the characteristic equation is what's left when you divide out those common pieces. Lambda squared plus 2 zeta omega n lambda plus omega n squared. And don't forget equals 0. That's our characteristic equation. And if you want to solve for the roots of this, so we're going to solve for this symbolically. We're going to use the quadratic equation. So that's minus b plus or minus the square root of b squared. It's probably been a while since you used this, right? Minus 4ac. A is 1. C is omega n squared. All over 2a. Well, a is 1. So we get minus zeta omega n plus or minus, let's see, the square root of 4 zeta squared omega n squared minus 4 omega n squared over 2. And if you simplify this, plus or minus omega n square root zeta squared minus 1. So these are the two roots . Okay, question for the audience. What's the time constant? How fast does this system decay? 1 over a. Wait, what's a though? Minus 1 divided by, what is that, an L times omega n? Oh, okay, the zeta. The constant of the first dot terms. MJ. MJ is right. So the definition of the time constant is always the same. Tau is minus 1 over the real part of my roots. So the real part is minus zeta omega n. Well, okay, actually, you know what? We're going to have to come back to this because this right here this will be the real part for an underdamped system. All right, we'll come back to this. We'll come back to this because it's important. Okay. This is how we're going to do this. Because, well, look at this table real quick. You're going to find out that you get different types of roots depending on the damping ratio. So actually, let's start with this third one. So let's say that the damping ratio is less than 1, but I should put this in here too. It's going to be greater, the damping ratio will always be positive. So let's say it's between 0 and 1. And then assuming that it's between 0 and 1, let's look at the roots and tell me what kinds of roots are these going to be. So the options are A, real roots, B, complex roots, actually I'll just give you those two options for right now. If zeta is between 0 and 1, what do you get, A or B? B. That's correct. So complex roots just mean that the roots have a real and imaginary part. If I plug in for zeta a number less than 1, what's going to happen? Let's say it's like 0.5 or something. I'm just guessing. I'm just making something up, I mean. Then if I take 0.5 squared, it'll be a number that's less than 1. I subtract 1 from that. That gives me a negative number. If you take the square root of a negative number, it's imaginary. So, let's go back to the table. You're going to get complex conjugate roots. And in that case, actually, let's say this. If zeta is between 0 and 1, you can actually write it like this. I'll use a different color. So this part won't change. Watch what I'm doing here. what I did is I switched the zeta squared minus 1 to be 1 minus zeta squared. So now, under here, under the square root, this will be a positive number, but I'm bringing this I to the outside to remind us that that should be an imaginary quantity. And this is where the damped natural frequency comes in, because this, as we wrote above, is equal to the damped natural frequency, and that's where it comes from. So I'll put like a little box around this. Oh my goodness, it's almost 3 o'clock already. Okay. If you get roots like this, if the damping ratio is between 0 and 1, we call this underdamped. That's what the pendulum is. So the general form of the homogeneous solution, so now we've done this a couple times. You know, you take e to the real part of the root, which is minus zeta times omega n times t. And then you multiply this by, some coefficient in front of a cosine times the imaginary part times t, plus another coefficient times sine of the imaginary part. Okay. Okay, let's keep filling in this table. What happens if this number, if zeta is bigger than 1? Do you get A or B? A. That's right, because this square root will evaluate to a real number, so you'll have minus zeta times omega n plus or minus a real number. So when it's greater than 1, we're going to get real distinct roots. That means that it's going to be two different real numbers. So I'll get 2 real roots. The classification is overdamped. And I have an example for this later. But the homogeneous solution looks totally different. Because the roots are real, there's no sine or cosine. So in this case, the homogeneous solution is a1 e to the lambda 1 t, where lambda 1 is like the first root, and it's just a real number, plus a2 e to the lambda 2t. So lambda 1, lambda 2, that's what I mean when I say distinct real roots. They're 2 different real numbers. All right, next, let's look what happens when the damping ratio is equal to 1. So these are my roots. What happens if you set zeta equal to 1? Real, complex, A or B? A once again. But do you get two different real numbers? Yes or no? No. Right? If zeta is equal to 1, then I have 1 squared minus 1. So I have the square root of 0 here. So I have minus zeta omega n plus or minus 0. So I'm going to have real repeated roots. That's what it's called. We call this critically damped. And in this case, the homogeneous solution is, it's still a little different than either of the other cases. It's going to have A1 e to the lambda t. And I'm not going to do lambda 1 and lambda 2 this time because there's only one root. A2 times t, that's the interesting part, e to the lambda t. And we know that lambda is minus zeta omega n in this case. All right, we're almost done classifying because we have 3 of the 4 types. The last one is when we set zeta equal to 0. Let's take a look. Actually, that doesn't really make sense, does it? If I set zeta equal to 0, then this would be 0. But this would also be 0, and my roots would be equal to 0. No, it wouldn't be. Yeah. My bad. Okay, yeah, you're right. It would be minus I. Okay, I'm glad you guys are here. Okay, if we set zeta equal to 0, the real part goes to 0, but the imaginary part is just equal to omega n times I, because this term remains. So in this case, you get purely imaginary roots. So there's no real part at all. This is called undamped because there's no damping whatsoever. So in this case, it looks like the underdamped, but it's missing any exponential decay because there's no damping to take energy out of the system. So it's cosine, and then it's not even the damped natural frequency, it's omega n, because that's the only thing left over. A2 sine omega nt. And remember, in this case, lambda 1 and 2 equals plus or minus the natural frequency times I. All right, I want to do this next example before we take our usual break, our little 5-minute break. Are you with me? We'll do this next example. We'll finish this page. Then we'll take 5 minutes. So let's look at the pendulum. We know that it's going to be underdamped because we've looked at this a lot. But now that we know some terminology, I want us to get the natural frequency, the damped natural frequency, and the damping ratio of the pendulum. And I'm going to show you 2 different approaches. So the first approach to solving for natural frequency blah 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 is to put the system in the standard second order form and then compare terms. Let me show you what I mean. Actually, I'm going to copy. I'm going to take this. So this was our equation for the pendulum. Copy. Paste. And bring it over here. This is already in the standard second order form because the standard second order form is this. 2 zeta omega n theta plus omega n squared theta equals 0. So basically putting it in the standard second order form just means make sure that there's a coefficient of 1 in front of that second order term. And we've done that here. And so what we can do, you can probably already see this. If I want to solve for the natural frequency, I compare these 2 terms. So omega n squared is 16.179. So my natural frequency is the square root of 16.179. I'm going to go over to MATLAB and punch that in. That's 4.0223, and the units will be radians per second. So that's the natural frequency of our pendulum based on the model. How do we get the damping ratio? Same way. Take this, and that's going to be compared to this. So 2 zeta omega n is 0.0215. So that means my damping ratio is 0.0215 divided by 2 omega n, and we already got our natural frequency is 4.0223 0.0215 divided by 2 times that. So that's 0.0027. I'll be busy soon, so I'll be taking my leave. Good day. Take care, all of you. Thank you for the stream. Thank you for stopping in, Falcon. Appreciate it. Okay. So that's our natural frequency. That's our damping ratio. And then I also asked for the damped natural frequency. Well, we have the definition for that. Omega d is omega n times the square root of 1 minus zeta squared. And this will usually be very close to your natural frequency. Let's see, I'm throwing it into MATLAB real quick. Yeah. for all intents and purposes, this is equal to omega n, because zeta is like 0.002. If I square that, it's like 0.00002. If I take 1 minus that, it's going to be basically 1. So unless you have a lot of damping in your system, the damped natural frequency will basically be the same. Makes sense? It's not too difficult. Okay, a second approach. Calculate the system roots and relate those roots to the standard second order roots. All right. Let's copy the roots from up here. Copy. Paste. And bring it over. So those are the roots of our pendulum. So I relate this to the standard form, which is this, minus zeta omega n plus or minus right? And we know that this is equal to omega d times I. So actually this method is easier for grabbing omega d because the imaginary part of your root is automatically equal to the damped natural frequency. Boom. Is that what our natural frequency was? Yeah, and you see the natural frequency was essentially that same number. Okay. So then I know this will be equal to this. So zeta omega n equals 0.0108. I know omega d, which is omega n square root of 1 minus zeta squared, equals 4.0223. I think this method's a little harder. Where did zeta come from? The zeta omega n? Like this? This came from if you find the roots of the standard second order form, you get this. Sorry. Or actually, I used this one. Oh, where'd the numerical value come from? That came from here. So I had the differential equation for the pendulum, and then I got the characteristic equation, and then I got the roots. So this is what I brought down there. Does that answer your question? Okay. Okay, so I guess so you have you have two equations here if you want to get the natural frequency and damping ratio. So so you got some choices to make. How about we do, let's do this. Omega n in terms of zeta. And then I'm going to substitute this in here. And that's going to give me 0.0108 over zeta times square root of 1 minus zeta squared is 4.0223. And you know what? I'm going to multiply both sides by zeta. So I'll bring this over here. And then I'm going to square both sides to get rid of the square root. So actually, this second method, as I'm going through it, it's probably not at all the preferred method. Because look how much work I have to do compared to the other one. All right, if we square both sides, 0.0108 squared. Then when I square this term, the square root goes away. 223 squared, zeta squared. Okay. Then I have 4.0223 squared plus 0.0108 squared zeta squared equals 0.0108 squared, right? So now zeta's the square root of all of that stuff. Let's see if I get the same answer. I mean, I should. Okay, divided by 4.0223 squared plus 0.0108 squared. Wait, I got a different... Oh, then I gotta take the square root of that. Jeez. Point. Okay. Yeah, you get the same thing. Good gravy. So if you solve that equation, blah, 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 you get that. So lesson learned. Use the first approach I showed you. I'm going to upload a homework right after this class is done. And one of the problems on there has you solving for natural frequency and damping ratio and all that stuff. So, I don't know. I suggest you use this first approach when you're doing that. All right, everybody, let's take a 3-minute break, a truncated break. Let's come back at 3:22. And we're going to introduce the spring mass damper system. And we'll just do some like more second order examples using this. All right, see you in 3 minutes. Whew. All right, people. Are you ready to get back into it? Get a drink of water. Have a little stretch or something. Oh, buddy. Or beer. Sometimes that's the solution. Sometimes that's the solution. Where's the Apollo 13 movie we were promised? Shoot. Yeah, we'll get through this class. Maybe right after class we should pull up some classic scenes. I really like that idea. I really like that idea. Okay, everybody. Here is like the classical mechanical second order system. This is what we always show in a system dynamics class. So what we have here is you just have what we call the mass, just like a block. And actually, you should think of this as sitting on a frictionless surface. So maybe it's just like sliding on some ice. All right. And then obviously this jaggedy thing is the spring, and this is a damper or dashpot. And then there's different ways to excite the dynamics of this system, but often we'll have a force that's pushing on it or pulling it. So let's break this down piece by piece, and then we're gonna use Newton's second law to write a second order differential equation for this. So first, the spring. The force that a spring creates is equal to the spring constant times the deflection of spring. So it doesn't matter if you stretch the spring or if you compress the spring, the force is going to be the same. It's going to resist that change in motion. So let's say, let's draw on top of this. Let's say I move this block just a little bit to the right. So what that would do is it would like slightly stretch out this spring a little bit, right? And let's say we just moved it a distance well, usually, let's just say it's S. I'm just getting confused over variables here. But if I move it a distance S, the spring is going to want to, pull the block back this way, right? And the magnitude of that force would be K times S. So simple enough. And if I alternatively push the block this way, I know this drawing is going to get a little busy now. Let's say I squish the spring a little bit. So it got squished now. And if it also got deflected a distance S, Well, then the force would go the other way, and the magnitude of that force would be the spring constant times s. In this drawing, we're going to assume that we stretched the spring a distance y. So that's what this coordinate means in the schematic. So I probably should have just drawn it that way, but whatevs. Okay, let's move on to the damper. So this works similar to the spring, but the force that it creates is proportional to how quickly you compress the damper. So it's proportional to velocity. So it's going to be c times velocity that damper is, I'll just say deflected. A very good physical analogy of this is, you guys have all used like a bicycle pump, right? Or you've pumped up a ball or a paddle board or something. But the faster that you push on that, the more it resists you. If you push it slowly, then it pushes very easily. So think of it like a bicycle pump. Okay, we're going to put all of this together into Newton's second law. Remember what Newton's second law says. Sum of forces equals mass times acceleration of a body. So in this case, we're looking at the sum of forces on our block. I opened the window a little bit in here, now this nice breeze is coming through. Okay. Is C the same thing as in the pendulum? Yes. Excellent question. This is a little different than the pendulum though, because this mechanical system is acting like translationally. I mean that nothing is rotating. Things are just moving side to side. So, in the pendulum, we would call that rotational damping. Like as it swings around that joint, it has some friction in there. This one is like a friction just from translating. But you're exactly right. It's the same thing. It's a force proportional to the velocity. Okay, so we're gonna have. We have 3 force generators on this mass. So I have the spring, I have the damper, and then I have like this explicit force, like maybe from somebody pushing it. So, and let's say that forces that are acting in the same direction as y, those are considered positive forces. So like this U force going to the right, that's a positive force. All right, let's add them all up. So the first force I'm going to consider is U. Then I'm going to look at the spring. Let's assume that we stretched the spring a distance y to the right. Well, then the spring, it's going to try to pull the block back to the left. So it's going to be minus k times y. So y is the distance it got stretched. K is the spring constant. But I used like a scripty K, so I should do that. Boom. So this is from spring. And then we're gonna have from the damper, so that's gonna be minus C, but it's based on how fast. So y dot is the velocity, which that the mass is moving and pulling on that damper. So this is gonna be the force from the damper. And then that's going to be equal to the mass. Why is the term negative? Because, wait, let me put this mass times acceleration. So, I'm defining positive forces to be the forces that are along the same direction as y. So the spring, if I move this mass to the right, the spring wants to pull it to the left. Right? If you stretch out that spring, it's going to pull you that way. So that's a negative force. And then if you move away from the damper, like think about as you pump a bicycle thing, if you, actually no matter which way, if you're pushing or pulling, it's always resisting you. So if I move this mass to the right, that dash pot's gonna resist it. A spring and a dash pot or a damper will always be resisting your motion. So if I pull it to the right, it's gonna resist it, so negative force. What's U again? U is this guy. It just represents some external force. So it's kind of like a spring and a damper. Those are some forces that I'm like specifying what is causing them. This U is kind of like a catch-all. There are valves in different orifice sizes that change the damping in the piston. Exactly. Spring and damper are in the same direction always. Ooh, when you say always, let me think. I don't know if I could say always. Oh, you're working on that stuff right now? That's how you know. Oh, that's perfect then. Ark is our resident expert on dampers. Yeah, in terms of a free body diagram, it'll always be the same direction. You're right. Okay. What I want to do is put this in the standard second order form so that we can get the natural frequency and damping ratio. So let's put it standard form. It's going to be, well, we're not at the standard form yet. I'll do it in like 2 steps. Equals U. Now, with this extra U term, this is not a homogeneous equation right now. But that's okay. We can still figure out what the damping ratio and all of that is. So now I'm putting it in the standard form. So that's 1 over m U. So let's just, to drive it home, the standard form is this. 2 zeta omega n y dot plus omega n squared y. So I'm comparing this to this, and I'm comparing this to this. So the natural frequency of a spring mass system, so omega n squared would be k over m. So the natural frequency is just the square root of that. Whoa, did you hear that? The wind like sucked the door closed. And it scared the crap out of me. Ooh. It was the wind. Jeez Louise. Did you guys hear that? And the wind will open the door too. That's because it opened it a little while ago, now it slammed it. Alright, that's natural frequency. Let's just leave that right there. Let's get the damping ratio. Your wind can twist doorknobs. Look. Maybe it wasn't totally securely locked in. Okay, 2 zeta omega n is equal to c over m. So, the damping ratio is c over 2 times m times omega n. And we already solved for what omega n is up above, so I could like substitute that in here. C over 2m square root of k over m. And you can even simplify that a little further. You can pull that m inside the square root, but it would be an m squared inside the square root. And you know, the 1m in the denominator would cancel it out. So you'd be left with this. So this is your damping ratio. Now, the interesting thing about a spring mass damper system is depending on how you change how stiff the spring is or how strong the damper is, you can get all of the different classifications of second order systems that we defined up above. You can get like underdamped, overdamped, critically damped. And that's where some design problems come in. A good example of this, if you're into cars, the suspension system in your car. A suspension system is very much like a spring mass damper system. Like let's draw like a bumpy road. I think we'll do an example of this later on, but you can have your, let's call this like the mass of your car. Well, they call the mass of above your suspension, they call it the sprung mass, like M sub S. So that's like your chassis, your passengers, that's you sitting in your car. You have your tire on the road, and we're just looking at one of the tires right now. But the connection between the sprung mass and the tire, there's a spring and there's a damper. And I think this is like the most popular example in mechanical systems of spring mass dampers. So as your tire moves up, it'll compress the spring, it'll compress this damper, and it transmits a force to the sprung mass. Oh man, and people are doing really fun stuff with suspensions nowadays. Are you guys familiar with the Bose active suspension system? I'm gonna have to show you this video. They never went anywhere commercially with this because I think it was just too expensive and too heavy. All right, we gotta watch it.
For 24 years, Bose worked on what it hoped would be a revolutionary electromagnetic.
Hold on, let's turn off the music.
Offering incredibly smooth ride for cars. The secret project was called Project Sound.
You should be able to build a car that basically flies along the ground, stays level all the time. So when you get to a bumpy road, it should stay level, and when you turn and brake, it should stay level. When we started the project, we actually started with a luxury sedan. So we bought two,
trucks now for
we put one to the side, and we
wow.
modified the other. This is the unmodified vehicle. That's what we're starting with. And it's gonna come down at a good rate of speed, and then it's gonna make a hard turn, lane change, and then we're gonna do a very hard braking maneuver. Then it'll come over these bumps, and then it'll slalom back. So now the white car, same make, same model, same everything, except completely modified suspension system.
Look at that. It doesn't even move.
We'll bring the cars down one after the other at a fairly slow clip. And I just want you to watch the body motion through them.
To finish
Amazing,
the
right?
demo, Bose gives us a look at a springy feature it had no intention of
What in
putting
the
into a
world is
passenger
that
vehicle,
system?
but it's
So
a
that's
fun way
an
to show off
active
how high-tech
suspension
and
where,
powerful the suspension system is.
Oh, watch this.
Is there a visual sensor then that can sense the depth of it?
You know, it's funny, right after we did it the very first time, I remember the person asking Dr. Bose that same question. And his answer was, he said, when I was 6 years old, I started studying magic. The first two...
Okay, because what's different about this suspension system is that it has actuators in here. I don't know exactly how they're mounted, but these can like apply a force at the right times to counteract the effect of like a bump in the road and whatever. So in that case, it's not, their suspension system is more than just a spring and a damper. What's the point of the damper? So the point of a spring is to bring something back to its original position. Like, think about it. If you stretch, I wish I had a spring here. Actually, this is a good example. Like, this has a spring in it. If you squeeze it, the spring right in there brings it back to where it was originally, okay? So that's the point of a spring. It wants to go back to its original position. The problem with springs, I mean, it doesn't happen in this system, but they oscillate, meaning they'll go like boing, 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 like back and forth. I don't know if you have this in your house, like the stopper on a door. You know what I'm talking about? If you like flick that thing, it goes. So that's a problem with springs, that they tend to vibrate and stuff. So what a damper does is it sucks energy out of the system so it doesn't go. So on your suspension, you get like the best of both worlds. You get the spring trying to, it gives some, how do you say this? Like one point of your suspension, you got coilovers in my car with adjustable damping. Shoot. You have a nice vehicle. One point of your suspension springs is to keep your tire in contact with the road. So like if your tire comes up, once you get over that bump, the spring pushes it back down to the road so that you maintain, contact with the tire. But the damper it takes out some of the energy, so it makes it a smoother ride. In very simple terms. People who are pros with suspension would hate what I just said, but it gets the main idea across. You're very welcome. Oh, why did so the reason I was talking about that is depending on the value that you choose for these, the dynamics change. And like when you're designing a car, that's very important because it's going to affect the comfort of the driver. It's going to affect the ability of the tire to stay in contact with the road. So when you're looking at the responses of these second order systems, think about what different responses are good for. The new Cybertruck has a cool new suspension system as well. Are you talking about the Tesla? Oh, I need to look into that. The Cybertruck is a bizarre, very cool looking thing though. I would love to have one.
Two things.
Okay. Let's turn this down a little. All right. So let's say that, let's put some numbers here. Let's say the mass is 1 kilogram. The spring stiffness is 987 newtons per meter. So that means if you stretch this spring 1 meter, it's going to give you a force of 987 newtons. So it's going to fight you. And this is going to be the dash pod. So the units for this are newtons per speed. So newtons per meters per second. So if you push this damper with a speed of 1 meter per second, which isn't like way too fast, it's going to push back 75 newtons. If you do like 100 meters per second, push it really fast, it's going to give you 75 times 100 newtons back. So it pushes harder the faster you push it. Okay. We're going to go through like this whole thing. We're going to look at the response of this. I'm going to code it up in MATLAB. And I think that's the last thing. We're going to be able to do. We're running out of time. All right. So those are the parameters. And then we're giving it some initial conditions. Like we give it some initial displacement. So this means the spring is stretched 1 meter at the very beginning. But the velocity is 0. So that means that the damper isn't producing any force at the very beginning because, well, it's not moving. It only produces a force if it has some speed. So we're going to solve for the homogeneous system response. So that would mean that U term up above is equal to 0. There's no force. Okay. Let's do this. So we're going to write out the differential equation first. Y double dot plus C over M Y dot plus K over M Y equals 0 because it's just homogeneous. There's no external force. If you plug in the numbers I gave you, let's just assume that you plug those into your calculator. Oh, actually, you don't need a calculator for this. C divided by M is 75 divided by 1. Yeah, we don't need a calculator for that. Plus 987 divided by 1. Okay, that's the differential equation. Let us get the characteristic equation. It'll be lambda squared plus 75 lambda plus 987 equals 0. Now the way that we're going to calculate the roots, start using MATLAB for this stuff. The more you use it, the more it'll be your friend. So so that's lambda squared plus 75 lambda plus 987. So the roots are minus 57.97 and minus 17.02. So we have two distinct real roots. Minus 57.98. We'll do that. Lambda 2 is minus 17.02. So these are not complex roots. Two different real roots. So that, well, that's one of the definitions of an overdamped system. It'll give you back two distinct real roots. So in the table up above, we have the general form of the homogeneous solution if this is the case. A1 to the minus 57.98 times t plus A2 e to the minus 17.02 times t. But does this equation assume that the dampening is linear from the start? You're exactly right. We're assuming it's linear from the start. The force from our damper is just C times y dot, but that's almost never the case. Yeah, but it's very good for modeling a lot of systems. And we're starting simple. That's a good place to start. You don't want to start with the most complex nonlinear case. All right, so next, we want to solve for what A1 and A2 are. The way we do that, we use the initial conditions. Oh, I planned on saving some space over here for that. Okay. So y at 0, we said that the spring was stretched to 1. So what we do is we take our general form and we're going to plug in 0 for time. So that's going to be e to the 0, which is 1, plus a2 times e to the 0, which is also 1. So that's our first condition. And then we have that our velocity at initial time was 0. How about down here we put what the derivative of this is, because we're going to need that. Not a problem to take the derivative of this. You just bring that coefficient down out in front. And if I evaluate this derivative when time equals 0, it's going to be minus 57.98 A1 minus 17.02 A2. And so we have two equations. Let's call this 1 and 2. And we have two unknowns, A1 and A2. Now you could solve this just by doing a simple substitution. Wouldn't take you long to do by hand. But as we do more complex systems, I want to show you a technique to use MATLAB to get this. So we're going to set up a matrix equation. And it's going to allow us to solve for A1 and A2. So the first matrix equation I'm going to put in here is equation 1. So it's 1 times A1 plus 1 times A2 equals 1. So that's just equation 1. You guys have all done something like this before, I'm sure. And then the next equation is minus 57.98 times A1. Oh, I'm going to run out of room. Minus 17.02 times A2 equals 0. So then the way to solve for A1 and A2 is you take the inverse of that matrix. So minus 57.98 minus 17.02. The inverse of this matrix times that right-hand side. And I'll take this on over into MATLAB. So what I can do, this is how you build a matrix. So the first row is 1, 1, and then you put a semicolon, and it goes to the next row. And now we put in the numbers for the next row. Minus 57.98 and minus 17.02. If you want to take the inverse of this matrix, let's just do it this way first. You can use I and V. So it'll take the inverse of that matrix, and then we multiply this by the vector 1, and then we go to the next row using a semicolon, 0. Boom. And that gives us A1 and A2. So I'll throw this code in the notes so you can come back to it. Let's go back here. So we calculated that in MATLAB. So A1 minus 0.4155, A2 was 1.4155. So our complete solution heck, I'll just write it right here. So I'm going to use this equation, and I'm just going to plug in A1 and A2. Minus 0.4155 e to the minus 57.98 t. Okay, now we got the A2 term. 1.1, I can't talk. 1.4155 e to the minus 17.02 t. And that is our complete homogeneous solution for this overdamped system. Let's plot this in MATLAB. So we're plotting response of second order overdamped system. And you know, the earlier steps we were doing, I would probably include that in this code, but heck, we already did it. But this is how you write it. Well, let's do this. A1 is minus 0.4155. A2 is 1.4155. Why don't we write it this way? Our first root was minus 57.98. Our second root was minus 17.02. y is a1 times the exponent of lambda 1 times t. And you know, I haven't even defined what t is yet. We have to do that, but let's come back to it in a second. And I can just copy this. This is another reason I like just writing out the variables. It saves me some time, because now I can just write this as a2 lambda 2. Ooh, here's a question. Let's say that I want to plot this system all the way to the settling time. So what would be the settling time of this system? And this is a little tricky because what did we define the settling time as for a second order system? Or a first order system for that matter. We said, well, let's start with the time. Well, the settling time is 4 times the time constant tau. And what is tau? Tau is minus 1 over the real part of the root. But in our case, we have one root is minus 57.98. One root is minus 17.02. So the question is like, which one would I plug in here? Because I would get very different answers if I did. So the rule of thumb, when you're talking about the settling time of a system that has potentially many roots, you choose the root that gives the slowest settling time. So my question for the audience is, if one of my roots is minus 57.98 and the other root is minus 17, which root gives the slowest settling time? Now, Jax wins flawless victory asks why. Okay, the reason is, I'll explain it like this with an analogy. Let's say you're hiking with a group of people. All right. And I say, when are you going to be finished with the hike? And I'm talking about the group as a whole. Do you base that on the fastest time or the fastest person in the group, or do you base it on the slowest person in the group? When you're the most tired, you move the slowest. I get it. So, answer to your question, minus 57.98. Actually, that is the faster of the two roots. So, think about roots as a group of friends going on a hike. The slowest friend dictates the pace of the hike. So, the slowest root is what we use to define our settling time, because it's going to bottleneck the speed of the response. The way to make this number tau as big as possible is to make the real part of the root as small as possible. Because if you take 1 divided by a small number, that makes the overall number bigger. You know what I mean? Like we'll test it real quick. If I have minus 1 over the real part, so let's say it's minus 57. So this one we'll come back to it. Minus 1 over minus 17.02. You can see that the bigger number in the denominator is going to result in a faster settling time here. So this would be 0.0172. 1 divided by 17.02. 0.0588. So this one here is like 5 times slower, basically. Give or take. So we choose this. Oh, if my pin will cooperate. This is slower. This slower. Choose this. All right, so we're gonna go back to MATLAB. Let's plot this. So our time constant tau, I'm gonna have its -1 over lambda 2, because that's my slower of the two roots. The settling time is 4 times the time constant. And we're gonna say that our time vector, so this is the times where MATLAB is going to calculate our solution. We're going to go from 0. If you haven't used the command linspace before, you define the number where you want to start, 0, the number where we want to end. How about we end at the settling time? And then you tell it the number of points that you want to generate in between. Let's do like 100 points. So it's going to generate 100 evenly distributed points between 0 and the settling time. And so now when I plug time into this equation here, we're going to solve for the system output at all of those points. All right, let's plot it. So I always make a new figure and then I plot t, y. I'm going to use circles for each of the points. I like to make the line width 2. I just think it looks a little better. I like to turn the grid on. It puts some like rectangular grid marks in the background. I always label my axes, time in seconds. Y label is y. And this is in meters. It's the displacement of this mass. I think that's all we need. Oh, and we're gonna make these circles red. Red circles. When I run this, it's gonna ask me to save this. I'll call it like in class 6/1/2020. That's today. And this is what it looks like. And look, because we plotted up to the settling time, boom. Wait. Let's try this though. What if I chose the settling time as the other one? You'll see that the overall system will not have settled yet because it only got down to 0.4. It didn't go all the way to 0. Actually, we can axis 0 TS 0 1. I'm just going to change the axis up a little bit so it's clearer. 0's at the bottom here, so it definitely didn't settle. How did you change all lambda values? Oh, I didn't change. Like you can see in the code, I didn't change lambda. I defined them up here. All that I did right now is I said, what if instead of choosing the slowest route for my time constant, what if I chose the fastest route, lambda 1? And then it recalculated my settling time and my time vector based on that. I'm gonna change it back to lambda 2. Boom. And now we see that the system actually did settle. We waited for the slowest friend to finish the race. An overdamped system won't have any oscillations back and forth. Yeah. Very cool. So, Guys, I'll put this code in the notes from today so that you can go back and use this as like a reference when you're plotting something. It shows you some basic commands. I'll wrap up the lecture right here, but I'm going to hang out here until 5 Eastern for office hours. I'm going to post these notes. I'm going to post our next homework, which will be due Wednesday. We'll try to keep it up. We'll stay engaged. And that's the plan. Thank you guys for your attention today. I hope you're enjoying it. I know I am. There's a lot of cool stuff to come. Dynamics is very applied. There's so many cool examples we can show you and that we can think about. So we'll have some fun this summer, you know? But it's definitely not easy. Yeah, you're very welcome. Dynamics is a very tough topic, so it's anytime you guys are struggling, know that